Hello everyone and welcome back to another mini concept, this time about acids and bases. So this one is mostly about acid and base theory and how to differentiate the Arrhenius, Bronsted-Lowry, and Lewis acids and bases. So let's start off by writing or drawing rather our Venn diagram for these bases. Because when a base is a specific type of base, it can also be classified as another type of base. So let's start at the smallest circle of our acids and bases. We have Arrhenius acids and bases. Arrhenius. Then encompassing Arrhenius would be Bronsted-Lowry. And encompassing all of this is the Lewis. Now, what are their differences? So let's start at the smallest shell. So Arrhenius acids and bases are, as mentioned here, determined by who is the hydrogen ion donor and who is the hydroxide donor. So an example of this would be in this type of reaction. Hold on, let me pick up color. So for Arrhenius bases, we could see this in the mixing or the reaction of NaCl. Oh no, not NaCl, rather NaOH and HCl to form H2O and salt. Now that's table salt. Now, how do we identify whether or not it's an Arrhenius base and Arrhenius acid? Well, as we can see here, so, oops, I'm gonna put these side by side here at the bottom. This is a double displacement reaction, if you notice. So the H of hydrochloric acid ends up going to water, and the Cl of hydrochloric acid ends up going to sodium. Now, excuse me, how do we identify which one here was the acid and the base? Obviously, since OH came from sodium hydroxide, the hydroxide ion came from this parent atom, this is going to be our OH donor. Now, where did the OH go? It reacted with the donated hydrogen from our hydrochloric acid. So this is our H plus donor. And the remaining is a salt, which is sodium chloride. So this side here is what our Arrhenius base is. Arrhenius base. And this side is our Arrhenius acid. There are multiple examples online, so I suggest you guys search, as that's what we're using so far. Now, what's another example of acid and base theory? We have excuse me, we have Bronsted-Lowry. So again, let's just label this. This is Arrhenius theory. Now, Bronsted-Lowry is when we're trading, or not exactly trading, but we're exchanging hydrogens. And what does this look like? Well, it can look like the reaction of ammonia and water. So what is ammonia? So ammonia is given by NH3, and then we add water. Okay, let's zoom this out a bit, and we'll change the color of this one. Make this let's make it red. Okay, there. So we have our ammonia and our water, and then we convert this into an H4. Now NH4 is an ion. NH4 is an ion, and it has a charge of +1. And we also form OH, or hydroxide. It's a bit too big there. So we form OH, and the charge of OH is negative. Now, let's put them on top of each other again, and let's identify who here was the hydrogen donor and the hydrogen acceptor. Because again, Bronsted-Lowry is just the exchange of hydrogen. So in this one, we see that the water, the water, um, the water is the one that donates one of its hydrogens to ammonia, and which here is the acceptor. Um, well, here the acceptor would be NH3. So NH3 is our Bronsted-Lowry base, while our water is our Bronsted-Lowry acid. Why? Again, it's because the water donates its hydrogen to ammonia, and ammonia receives the hydrogen, which makes it the base. So that's how we determine a Bronsted-Lowry reaction, or a Bronsted-Lowry acid and base. Now, how about for Lewis acids and base? Now, Lewis acids and bases, they encompass every type of acid and base, as mentioned earlier. So, this is more to do with electron structure, and that might be an unfamiliar topic to some, but it's just let's just go over the basics of how electron bonding works, right? So one of the examples I have here is excuse me, the reaction of, okay, hold on, I'm gonna shrink this. Okay, there. For Lewis, we have to draw, so we're gonna have a lot of space here. Right now, for Lewis, we have an example of boron trifluoride plus ammonia forms boron trifluoride and NH3. So that's literally it. And how does this work? Well, in Lewis acid and base theory, an acid is an electron acceptor. So our acceptor here would be something that needs to have a complete octet. First, let's draw the structures of these. So the structure of boron trifluoride is given as such. So boron has 3 valence electrons, and fluorine has 7. So we can draw the lone pairs here. This is going to form one bond, fluorine and fluorine. So there, we can actually remove the dots here just for organization. And we're gonna make this react with ammonia, which has 5 valence electrons. So H, H, H. As you can see, now ammonia has a complete octet. However, boron trifluoride doesn't. How do we know? We can count. So each line is equal to 2 electrons, and we want each of these parent atoms to have 8. So now boron has only 6 electrons, while nitrogen has 8. It has 8 electrons. Now which one here would need to accept an electron pair? Since we know that boron trifluoride needs an electron pair, we can say that this one over here is actually our Lewis acid. Because again, a Lewis acid is an electron pair acceptor. So this is our acid. And this is our base. Because this will form boron, fluorine, sorry, not fluorine, nitrogen. This is H, 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 and H. So now both of them have complete octets, and it's to do with the transfer of an electron pair. So Lewis acids and bases are really more of a structural analysis compared to the formula analysis that we get from Bronsted-Lowry and Arrhenius bases. Now, how do we know that how do we know that all Arrhenius acids and bases are Lewis acids and bases? All Bronsted-Lowry acids and bases are Lewis acids and bases, and they're all exclusive to whichever one is inside, right? We can identify the common characteristics of these theories, right? So, for example, let's start with Arrhenius theory. So, in Arrhenius theory, we donate OH, and we donate um, H, right? So we have two donations happening here. We have a hydrogen ion and we have hydroxide ion. Now, in Bronsted-Lowry, which an Arrhenius base is also a Bronsted-Lowry base, a Bronsted-Lowry base is an acceptor, right? Is an acceptor of hydrogen. So let's go back here. Let's take a look at our Arrhenius acid and base. Our NaOH accepted a hydrogen ion. That's why it was able to form H2O, right? Now, how about our acid? Our acid here was an H plus donor, which was our HCl, and that just so happens to be as well our Arrhenius acid. So we can see that they actually align, right? So our Arrhenius base is also a Bronsted-Lowry base. Now, how about, is it a Lewis base and acid? Well, yes, it is, because when we see here that when we see that Arrhenius acids are the ones that donate, right? They need to accept electrons this time. NaCl here, so NaCl is given by, it's an ionic bond, right? So Cl has seven electrons, and Na has one free electron here, one valence electron, and they're going to have an ionic bond. So now this is going to be our electron acceptor. This one is an electron acceptor, meaning that HCl is still our Lewis acid, and our NaOH is going to be an electron donor. In what form? Well, it gave away its sodium, right? And since it gave away its sodium, it became the Lewis base. So that, I think, wraps it up for this video on acids and bases. Now, it's really quite confusing if you don't understand the dynamic of electrons and how they're important in bonding. Now, I suggest you guys search up some simple tutorials on how to draw structures, how to draw Lewis structures in particular, because these will allow you to understand how an Arrhenius base becomes a Bronsted base and a Lewis base at the same time, how an Arrhenius acid does the same, and why they're sometimes exclusive of one another. And without it obviously goes without saying, you need to know how to make the structure in order to analyze a Lewis base. So that's it for this video, and I hope you guys learned something. If there are any questions at all, I'm aware that this might be a confusing topic, so please let me know in the comments if there's anything. Thank you everyone for watching, and goodbye.